In progress.
Sure. All right. We are live. We are going live.
Can you give us a countdown?
Yes, Ella, we are live. Just wait for a few minutes. People to join.
Okay. Just let me know when I can start. So, hello and welcome everyone. A very good afternoon to everyone. I am Ella, and it's a pleasure to welcome you all on behalf of eMobility Plus and the First View Group to today's insightful webinar on improving thermal management of batteries with COMSOL Multiphysics. First and foremost, we would like to extend our sincere gratitude to our partner, COMSOL, for their continued support in making this session possible. Before we dive into the session, I'm pleased to introduce our esteemed expert speaker, Dr. Meenakshi Fatke. Application specialist at COMSOL, Dr. Meenakshi holds a bachelor's degree in chemical engineering from KBCNM University, Jalgaon, a master's degree from Sardar Vallabhbhai Patel National Institute of Technology, Surat, and a PhD from the Institute of Technology, Bombay. Following her PhD, she worked on developing green steel technologies as a postdoctoral fellow. Currently at CAMSOL, she specializes in chemicals reaction engineering and multiphysics modeling. Now, a brief overview of today's session. As electric vehicles and energy storage technologies continue to scale, efficient thermal management of battery systems is becoming critical, not just for performance and reliability, but also for safety and lifespan enhancement. In today's session, Dr. Meenakshi will demonstrate how multiphysics modeling, combining electrochemistry, heat transfer, fluid dynamics, and structural mechanics, can be effectively used to solve real-world battery challenges. She'll also introduce how COMSOL's battery design module streamlines the creation of high-fidelity battery models and accelerates innovation in thermal management. Following the presentation, we'll host a Q&A session where Dr. Meenakshi will respond to questions submitted via the Q&A box. So feel free to drop in your questions anytime during the session. Before we begin, we'd like to play a short video that highlights how COMSOL is supporting innovation across the automotive industry. May I now request the team to kindly play the video?
Developing designs and performing experiments virtually is both cost and time efficient. With COMSOL Multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The COMSOL software offers all three, and the true advantage of COMSOL Multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in COMSOL Multiphysics gives you the tools to build your own simulation apps. The Startup Wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted inputs and outputs, report generators, and more. This way, you can spread the advantages of simulation to colleagues and customers by compiling your apps as standalone executables via COMSOL compiler, or by making them accessible by web browser via COMSOL server. Understand, predict, innovate, and optimize your processes and designs with COMSOL Multiphysics.
Thank you, team, for that insightful video and for showing us COMSOL's role in advancing automotive solutions. Now it is my pleasure to hand over the session to our speaker, Dr. Meenakshi. The floor is yours, ma'am.
Thank you, Ella, for a nice introduction. So, first of all, thank you so much, everyone, for taking out time and to attend this webinar on topic improving thermal management of batteries with COMSOL Multiphysics. Let's begin this journey. We will talk about the various simulation aspects of the battery modeling with COMSOL Multiphysics. So whenever we talk about batteries, so battery is a storage system for energy, uninterrupted energy supply. So now we know that every day, due to advancement in various technologies and machine learning tools, so we are constantly automizing the process, and for that we need a consistent uninterrupted power supply. For that case, we use battery as an energy storage system, which will give us a supply when there is an interruption in a electrical energy given from the grid. So in that case, again, when we are talking about pollution control and climate change, every government is pushing for the renewable resource energy as a supply, and to make it uninterrupted, again, the energy storage systems such as batteries are used for all these applications. So that's why batteries and different technologies of batteries are a talk of town everywhere. But in batteries, the thermal management is a key aspect, and it is very critical when it comes to delivering a consistent energy supply and giving a good performance and efficient performance of a battery. So we need to learn about the thermal management of batteries. And when we talk about thermal management of batteries, so in batteries, these batteries typically can be applied in many tropical countries like India, where our temperature often goes beyond 40 degrees Celsius. However, the most battery which are used in market are lithium-ion battery, which operates efficiently only in range between 50 degrees Celsius to 35 degrees Celsius. And also in northern countries where the temperature goes below 0 degrees Celsius, again, this range is not achieved. So to maintain this efficient optimal operational range of temperature from 15 degrees Celsius to 35 degrees Celsius, efficient cooling as well as heating strategies for battery energy storage systems are required. And when it comes to modeling these strategies and making this thermal management of battery energy storage system efficient, we need to simulate various scenarios where we need to do a thermal analysis over this system, and where the multiphysics phenomena come into picture. Because whenever batteries are in motion, whether they are delivering energy or they are taking energy for the storage, like either they can be in a discharge mode or charge mode. In both the cases, the multiple electrochemical reactions happening inside the batteries can act as an energy source, a heat source. And if this heat is not dissipated in time, it causes the heat hotspot generation, temperature increase inside a battery system, which could lead to a temperature increase beyond the optimal range, which could accelerate the various aging phenomena of battery and could lead to scenarios like thermal runaway. To avoid such scenarios, to mitigate such situations, to study these different scenarios, the simulation tool like COMSOL comes into picture, where we have facility in combining multiple physics in a single interface. So what I mean by multiple physics is because when the electrochemistry of battery is happening, the charge transport inside a battery, ion transport inside the battery, again, when the thermal management is into the picture, then how the thermal temperature distribution inside the battery. So various physics like heat transfer, fluid flow, battery chemistry are into picture, and we need to consider all of them while simulating a real case scenario of thermal analysis of battery. For all these purpose, we build different models in COMSOL with our different functionalities of COMSOL. It is, you can see different strategies. You can study the thermal analysis of battery and do a thermal management for your battery energy storage system. So in this particular today's session, we'll see how we can study the battery energy storage system and their thermal management in various aspects, whether it's from the chemistry point of view or it's from the point of view of structural or thermal analysis of battery. So moving on, we'll also talk about various cooling methods that can be modeled in COMSOL with the help of different interfaces offered here in our tool, like air cooling of battery energy storage system, or liquid cooling, or the most advanced, most talked in the market, which is a phase change material technology for cooling and maintaining the temperature of the battery pack. So all these different cooling strategies we can discuss in this today's session. So before moving further, going ahead further, I would like to launch a poll question so that I'll get to know you all, and we'll deep dive into today's session. We'll talk about modeling, how to model a battery and do a thermal analysis. I'll take a moment, please, everyone, take part into this poll, and then we'll deep dive into the session on the simulation of the batteries and their thermal management with COMSOL Multiphysics tool. Okay, thank you everyone for taking part into this poll. So moving on, when we are talking about the simulation and modeling of the battery, so what different physics we need here is to simulate a battery performance. We have a battery pack interface in COMSOL, which is based on the modeling technology where we consider different losses inside a battery when it's in operation, like ohmic losses, activation losses, concentration over potential losses. Also, when there is a particle diffusion inside the particles of the porous structure of batteries, so we can consider that loss, as well as when it coupled with the various aging phenomena, how the capacity losses are affecting the battery performance. All these different scenarios we can consider in the battery performance and battery pack interface, and we can simulate a battery performance in COMSOL. When coupled with the heat transfer, we have interface called as heat transfer in solids and fluids, where we can consider the heat generated due to battery, which is either it can be in a discharge mode or charge mode, which could lead to a different losses, and it contributes to the heat generated inside a battery. So we can consider all those heat sources in battery and consider them in a heat transfer physics when it coupled with the heat fluxes at the boundaries of the battery pack. It gives us a real-time temperature distribution or thermal analysis of a battery. And for the cooling strategies, when we do a liquid cooling or air cooling, how the fluid dynamics, like such as if there is a air cooling and we are blowing air on the battery pack, how the turbulent nature of that air blown on the battery pack affect the thermal temperature distribution, how it affects and facilitate the heat transfer from the boundary of this battery pack. So for that case, we couple this heat transfer with the fluid flow, and we get coupling of non-isothermal flow multiphysics, which combined with the battery pack interface gives us a real-time temperature analysis inside a battery pack. And sometimes when we are using a liquid coolant as a cooling strategy for a battery, there might be a addition of one more physics which could be required, that is heat transfer and a fluid flow inside a pipe. And all these different interfaces, how to use them, moving on, we'll see in upcoming part. But before going that, we'll first look into the battery pack interface and how batteries can be modeled with the help of COMSOL. So in battery modeling, we have different options to model these batteries. For the approximated approach or the fastest approach, we can go for a 0D approach, or which is also called as lump battery model approach. But if you want to go in details of the battery, how the battery various components are behaving, how the charge transport and ohmic losses are happening. So in nutshell, if you are interested in going into more details of the battery chemistry, you can go with the 1D, 2D or 3D geometrical approach of the battery modeling, where you can either build a geometry inside a COMSOL, or you can import it from the other CAD tools. So depending on the scale of your modeling, like micro scale, cell scale, or pack scale, you can choose any of this modeling approach, and then we can build a battery chemistry and see how the battery is behaving while it's given a different dynamic load, such as charging, discharging with different C rates and all. So talking about different chemistries, particularly for the chemistry of lithium-ion batteries, we have dedicated interface which considers Newman model for modeling these batteries. The predefined formulation is already there for lithium-ion batteries. Apart from that, we also have a dedicated interface for lead acid battery as well, where the porosity change, how the in the lead acid battery, how the concentration changes of sulfuric acid, how it affects the porosity, and how the porosity affects the charge distribution inside a lead acid battery. All those predefined formulation for lead acid batteries is also there along with the lithium ion batteries. Apart from these two famous, if you are interested in modeling different batteries like nickel hydroxide battery or zinc bromide battery or metal air batteries. So all different chemistries can be modeled in COMSOL, because all sets of equation required for the battery chemistry modeling, such as Nernst-Planck equation, Onsager-Stephan equations, are already there. The formulations are already there, just by choosing proper boundary conditions, geometry, and sets of different domain conditions, we can model any kind of battery chemistry which is available in the literature and in the market. So all these, and here also you can consider different levels of the modeling, like micro scale to cell scale to pack scale. So talking about this is one of the example apart from lithium ion batteries, where we are showing that we have also feature for lead acid battery, nickel metal hydroxide battery, vanadium redox batteries, where we can consider different chemistries, and we can do a study which can be time dependent stationary. So for all these chemistries, the sets of equations we use are the equations for electrochemical kinetics, to depict the electrochemical kinetics of the various reactions happening on the positive and negative electrodes of the batteries. So for that, we have Butler-Volmer equations, which consider these kinetics and electrochemistry. And to make it temperature dependent, we have Nernst-Planck equation, where the equilibrium potential will be updated every time with change in temperature. So that's how our kinetics is coupled with the thermodynamics. In thermodynamic database of COMSOL, we have properties such as density, viscosity, diffusivity, equilibrium potential, all the properties required for the various analysis. So all the thermodynamic properties and their different models are there in our thermodynamic database. Apart from the kinetics and thermodynamic, when it comes to the transport phenomena such as mass transport or charge transport inside a battery, for this diffusion and migration of charged ions, we have various equation sets for these typical conditions when it is occurring through a porous structure or free flow structure. Apart from that, for the thermal analysis, in addition to the diffusivity, viscosity, density change, and the equilibrium potential change, we also have this for the consideration of thermal conductivity and how it's subjected to various temperature, how it affects the Joule heating inside the batteries, how it affects the heat generation inside a battery. We can consider here the multiple levels of fidelity we can apply by considering a constant thermal conductivity or anisotropic nature of thermal conductivity. So all sets of formulations required, from whether it's from kinetics or it is from thermodynamics or it is transport related or heat generation related. Heat generation related physics we can consider, and all sets of equations will be there. By using appropriate boundary conditions, we can set our model in a detailed, more accurate level, and we can depict the real case scenarios for the battery performance. When we talk about the various scales of these batteries, as I mentioned earlier also, that from micro cells to pack scale, we can model with the help of COMSOL. In micro scale, it means when you are developing, you are new into the battery chemistries and you wanted to develop a new chemistry of a battery, where you are mixing different cathodic material and cathodic material or different particle size distribution is there. So in detail, heterogeneous structure of the electrode you have with different characterization tools, and you have some microcity images. You can build in, you can bring in that kind of detailed geometry and see how exactly the porosity at different levels of the electrodes is affecting the electrochemistry of and overall battery performance. So that much in detail, more fidelity modeling can be done with the help of heterogeneous macroscale modeling. But if you are just interested in knowing how on the cell level, when we put positive electrode, negative electrode, separator, current of conductor, everything in one system, and how after creating such geometry and giving different formulations, such as in case of lithium ion, when you are choosing a different cathodic material, how it affects the cell level performance of a battery, that you can do in a homogeneous level scale. What we do here is we do a porous when we have a different porous structures for positive electrode or negative electrode, we homogenize the properties and we do a cell scale modeling. But when we are talking about pack scale, so so much details from the micro scale and cell scale is not required, because when you buy a battery from the market, you are not developing your battery, you are not a battery OEM, battery manufacturers, and you are simply buying that battery, and just you are interested in doing a cell level study and improvement of thermal management in pack level. So in that pack scale, you are just interested, you just know, you don't know about the battery chemistry, but you just have the observations that how the open circuit voltage is changing with respect to state of charge. So in that level, we just you are just interested in knowing how the battery will perform after giving certain load of charge discharge cycling. So in that scale, we go for a lump type of modeling, which is the most simplified approach, where we just solve algebraic equations, and then we get to mimic the performance of a battery, how it will behave over the time. So such kind of pack scale modeling, which comes under a lumped modeling, can be done with the help of COMSOL. These are the different scales when it comes to modeling. And what these scales offers is, whether it's a micro scale or a cell scale, you can do all kinds of you can use all sets of electrochemical equations and do a different studies like electrochemical impedance spectroscopic studies, whether it's micro scale, cell scale, or pack scale. In pack scale, usually we use the lumped scale modeling, where we take a 0D approach for model of battery performance to mimic a battery performance, and how the battery's operation is in operation generates the heat, and how to dissipate heat, how to do the thermal management. We go for this pack scale lumped modeling. So today in this session, we'll focus on the rightmost pack scale model as shown over here. Let me just highlight that part. So we'll focus on the pack scale model, where we'll use the lump modeling of the COMSOL, and we'll couple it with the three-dimensional thermal analysis, heat transfer physics, and we'll get to know that how exactly the temperature distribution is happening inside a battery, and how we can improve the thermal management, which is the topic of a discussion for today's session. And when we are talking about the various types of studies, we can do a stationary study, time-dependent study. We can do a dynamic cyclic study, where we are giving continuous charge discharge cycling, or we can mention a different discharge rate, and you can see how the actual battery is performing with related to those different charges. So in the first figure, you can see that here example of dry cycle for lithium ion battery, when it given a different charge discharge load, how it behaves, how the potential of individual electrodes changes with respect to time is shown over here. And other studies like electrochemical impedance spectroscopic studies, which are done usually to calculate which resistance is offered more in different arrangements. So such kind of Nyquist plot or Bode plot we can plot by doing a EIS studies, which is a frequency domain formulation to calculate the various resistance offered in the by various stages of the batteries. And then we can also build a cyclic voltogram and different charge discharge cycling. So depending on the necessity of modeling, you can choose any study types, whether stationary or parametric sweep or parameter estimation. So many times when you buy battery from markets, so you don't know about exact parameters of those batteries. So what we can do, we have one parameter estimation strategy option given in a battery physics. It comes with the battery physics. So what we do is you can assume some parameters while building a model in the initial phase, and once you have some experimental observation, you can try to fit the model results with the actual experimental data and do a back reverse engineering to calculate the parameters by using various optimization techniques like Levin smart curve or Bobby QIA. So such kind of different gradient based strategies and options are there to calculate a parameter estimation with the given experimental observation. So such kind of different study types you can do with COMSOL, not only just building a time dependent how the battery will behave, but how the calendar aging will affect the battery performance, how the different parameter affect the performance of a battery. That all kinds of studies you can do with the help of our tool. So moving on, we'll see what is the difference between when we switch from a cell to pack scale, what happens. So when cell scale, we are actually simulating for a different component, whether it's a porous electrode, positive electrode, negative electrode, and then how separator, current conductor, all layers or different components of the battery are affecting the cell performance. And then we can shift towards a more lumped model approach for a pack scale. And in that we wanted to see how this shift from cell scale to pack scale, when we are approximating some of the things and we are not going in details of the every component of the battery, how it affects the overall modeling of this, overall prediction from these different approaches from cell to pack scale. So we did one study that we'll see discuss later on. So in the pack scale, when we talk again in pack scale, as I mentioned, it is based on the lump modeling and full scale modeling, or that is 1D modeling. So different kind of geometries for pack scale we can consider, from cylindrical pouch cell to prismatic cells. So all kinds of different options are there to consider when it comes to pack scale. And you can consider different arrangement for the power output, like series connection, parallel connection, and how it gives a different capacity and potential when we are arranged in a different manner. And when we do this coupling between the battery performance with the heat transfer, by considering different losses, we get the thermal analysis. And to make this comparison, we build this model where we consider the pack scale lumped model to the actual single scale detailed Euler-Fuller-Newman model. So when we did a comparative study in order to see how the computational, when we save a computational time by choosing a lumped modeling, how much of accuracy we are compromising on. And when we did such kind of study, we got to know that even our the lump model, which is the fastest 0D model, gives a similar result as compared to the more detailed Euler-Fuller-Newman model. So it shows the capability of COMSOL when it comes to battery performance. Even though it is a fastest 0D approach, still it gives a real life prediction of the battery performance. This example demonstrates our capability when it comes to battery modeling and predictions. So before diving into more aging phenomena, how it affects the thermal management, I would like to launch a second poll question, and I'll take a moment so that you can answer that. So after discussing various approaches of the battery modeling, whether it's from a micro cell scale to pack scale, and different kind of studies we perform in COMSOL, you can perform with COMSOL. Now we'll go into the details of the battery aging phenomena and thermal management. We know that in batteries there are various parasitic reactions happens which causes the reduced in battery performance and capacity fade of the battery, such as plating of the lithium plating and short circuiting. Again, short circuiting raises the temperature, which can cause a fire hazard in a battery pack. So such kind of various aging phenomena, plating, short circuiting, gas evolution when it comes to um, thermal runaway, then side other decomposition reaction, side reaction, loss of electrolyte or SCI formation, or in when the lithium ion is shuttling in between two electrodes. So how it affects, creates the mechanical stresses inside a battery, how it accelerate the mechanical degradation of a battery after n number of cycling. So all kinds of different aging phenomena we can consider in COMSOL by considering different side reaction for those particular cases, such as mechanical degradation or gas evolution. And ultimately, all these side reactions are exothermic in nature, which causes a temperature rise inside a battery, so which can leads to a temperature rise. And then that's how we can couple these different capacity fade phenomena or aging phenomena and do a thermal analysis of a battery, which is critical when it comes to thermal management. So all these phenomena of short circuiting, gas evolution, thermal runaway, chemical combustion, the propagation of thermal runaway, all this we can model here with COMSOL, and one few of the example we'll see in upcoming part. So when it comes to thermal management, so we need a heat transfer physics coupling with the battery pack coupling. So in that case, in heat transfer mechanism, all three different modes of heat transfer from conduction, advection to radiation, we can consider all three different mechanisms of the heat transfer. So for typically for the conduction, where the thermal conductivity for because in battery structures are highly porous in nature, and due to the solid and the fluid part inside a battery, that is porous structure of the battery, there can be different scenarios of thermal equilibrium, thermal non-equilibrium. Then thermal conductivity can also be isotropic, it can be anisotropic. In a different plane, it can have a different value. So such the anisotropic nature of thermal conductivity, thermal equilibrium, non-equilibrium, or linear nature of thermal conductivity with respect to temperature, or non-linear nature of thermal conductivity with respect to temperature. So much different details when it comes to conduction through different layers of the battery. So we can consider all these different scale, like scale of modeling to the how much details or fidelity of modeling you can decide, and we can consider different scenarios of thermal equilibrium or anisotropic nature of thermal conductivity, and we can mimic or we can get a thermal analysis inside a battery which will mimic a real-time temperature distribution in an actual battery pack. Apart from the conduction, other phenomena are important when it comes to thermal management are advection and radiation. In advection usually is coupled with the fluid dynamics as well. So conjugate heat transfer with fluid dynamics. The fluid dynamics can be a laminar or turbulent in nature. It can be a compressible or incompressible. In liquid coolant, it will be incompressible, laminar or turbulent flow. In case of air cooling, it can be a laminar or turbulent compressible flow. So such kind of conjugate heat transfer coupled with coupled with flow dynamics gives a conjugate heat gives us a real-time temperature distribution which is affected by the advection phenomena. So all such kind of scenarios from conduction, advection we can consider, and if you want to go into further more details of the thermal analysis, you can also go for a radiation mechanism, how it affects the thermal distribution inside a battery pack by considering different options like surface to ambient radiation or surface to surface radiation. So here we have in COMSOL all three different kinds of mechanisms we can consider, and then which contributes to a thermal analysis of battery. But what exactly causes a temperature rise inside a battery are these different heat sources, because all the electrochemical reaction when they are taking place, they are exothermic in nature, which gives us a temperature rise which comes under activation over potential losses, and due to which the temperature increases again because these charge is transporting and ions are transporting inside the various components of the battery. And we know that any metal conductor which when it transport the charge, it can give us a joule heating in a conducting part. In non-conducting part, when the ions are moving, it can also lead to a rise in a temperature. Such kind of different scenarios, from joule heating, electrochemical reaction heating, to a heat of mixing, because there are various temperature concentration gradient inside the battery, the various components, which can also act as a energy source due to heat of mixing. So all different energy heat sources, like from joule heating, electrochemical reaction heating, heat of mixing, we can consider. In all of these, most dominant is the joule heating, which we can consider always. And for the more federal model, we can also consider other scenarios like electrochemical reaction heating and heat of mixing. And then when lithium ion is constantly shuttling between the two electrodes, the entropy changes, and this can also act as a energy generation or heat generation inside a battery pack. So all different scenarios of heat sources we have considered in our electrochemical multiphysics coupling of battery module, and which gives us a real-time thermal distribution inside a battery pack. So now we'll look into the one of the example we modeled in COMSOL. The geometry you can see here. This is a huge battery energy storage system, which is supplying 360 voltage, which has a capacity of 360 voltage, which has 14 cells stacked in 4 lines in 8 different modules. Such kind of huge geometry you can create in COMSOL. So here prismatic cells are used, and below the batteries, we have a coolant channel, which are shown over here. These serpentine coolant channels are facilitating flow for a cooling fluid, which takes the heat generated from the battery and it cools down the battery. So such kind of different geometry, intricate geometries you can create with COMSOL, and as the detailed plates, which are actually closer designed towards what we get in a market as a cooling plate in various electric vehicles. If you see a battery structure of or a battery energy storage system of electric vehicle, you will find this kind of serpentine channels located below the battery packs. So we have considered such a real case scenario, and where we are using a coolants such as 50% ethylene glycol, and how this coolant help us in maintaining the temperature of this huge battery energy storage system that we'll see in this figure. So the model setup looks like this, where for the battery pack performance analysis, we have battery pack interfaces used, where we are using different losses caused by activation over potential, ohmic over potential, or concentration over potential, which contributes to the or act as a heat source inside a battery when battery is it is in operation. And when this battery pack operations are coupled with the heat transfer in pipes and heat transfer in coolant liquid, which is flowing through a different serpentine channel, we get a model which is shown over here. And such kind of model gives us a real-time scenario how the temperature will be distributed inside a battery pack. Let me just show you. So in this case, to make it more realistic in the heat transfer interface, we have also considered the battery layer. So when I was mentioning about the different mechanism for heat transfer, I mentioned that in the conduction, that is thermal conductivity can be different in different planes. It can be high in plane, or it can be low in a thermal through plane. So such kind of different anisotropic nature of different battery layers we can consider. The example is as shown over here. For this typical example, you can see that the battery configuration here is at a flat parallel pouch cell we have considered, and in which the different layers of the battery is offering different thermal conductivity, which affect the temperature distribution for this huge battery energy storage system. So we have considered that much of accuracy while modeling this type of energy system. And this option of predefined battery layer configuration offers us a capability to consider such scenarios. We also have other layer configurations, such as a cylindrical or a prismatic cell configuration, because we know that different geometries of the batteries can have a different layer configuration which affects the temperature distribution, because in cylindrical cell, the radial distribution is most important compared to other distribution. So by considering such different configuration, we have created this predefined option in battery layer, which gives us a real-time thermal conductivity of different layers of the battery, and which makes it easy for us to predict the temperature distribution inside a battery. So this is one of the example where we have showed the liquid coolant. So what if there is a case of a thermal management using a phase change material. So now the earlier example was for a prismatic cell, but this example is for a cylindrical cell. So in what is happening is in between the gap of this cylindrical cell, we have considered two options. One is that the air is filled, or second option is that phase change material is filled. So we know that whenever some substance changes the phase, so what it does is it takes the latent heat for the melting and it doesn't allow the temperature to rise inside a system, because that heat generated from the battery will be used for the phase transition, so which causes a reduced temperature inside a inside a pack of a battery, and which gives us a good thermal management inside a battery. So we wanted to study these different management phenomena. So we consider the case where the air gap between different cylindrical batteries is filled with air compared with the phase change material, and how it affects that. So we found that towards in a demo part also, I'll demonstrate this particular model where I'll show you that for the heat transfer physics, we considered two different cases from air to phase change material, and how it phase change material effectively manages the temperature compared to the air one, and how it's more effective compared to the air strategy, which is just a usual case of a battery pack configuration. So moving on, the different strategy after the liquid coolant strategy and this phase change strategy, next comes is the air cooled battery energy storage system strategy. So here what we are doing is, so apart from those two physics, here what we are doing is we are blowing air on the surface of the battery modules, and due to the turbulent nature of blown air, the coupling between the fluid dynamics and the heat transfer, giving us a real-time temperature distribution inside different models. So this is one of the, again, a different technology when it comes to thermal management. So typical setup required here is we need a battery performance battery pack interface coupled with the turbulent model and heat transfer model. So in here in the multiphysics coupling, here we see that fluid dynamics is coupled with the heat transfer. That is, here you can see that turbulence model is coupled with the heat transfer, and it gives us the actual temperature distribution on the surface of the batteries, and how we can maintain the battery temperature is shown over here, where we are using a non-isothermal flow and heat transfer conjugate coupling. And the formulation and equation behind that are shown over here, where we are applying the thermal wall function, and hence we get a temperature distribution in this battery pack. Moving away, so after defining these different three technology as a liquid coolant or phase change material, or as a air acting as a coolant, so what happens when we fail to do a thermal management? So this is a worst case scenario when we are failing. We did a thermal analysis and we find that there is a situation which can cause a thermal runaway, and now we want to mitigate this kind of scenario. So how we can model that with the help of COMSOL is with the feature called as thermal event, which is there in COMSOL, to consider the thermal runaway in a battery. In a thermal runaway, when this situation happens, we know that various decomposition reactions starts dominating the battery electrochemistry. It increases the temperature and pressure inside a battery, which causes the because all these reactions are highly exothermic in nature, it acts as a heat generation source, and when this heat is not dissipated in time, that means we have failed to do a thermal management of the battery pack. It causes a failure of the battery of the one cell, and then when it propagates to a neighboring cell, it causes a thermal runaway propagation. And how to model that with the COMSOL is shown over here. In the battery pack intercept itself, we have option of considering a thermal event option, where we give a thermal event failure of a one battery cell, and when it propagates to the other cell, which is a thermal event 2. So both thermal runaway of a single cell and propagation to a next cell, we have added this feature into the battery pack interface. So we can consider that case, those scenarios, and due to which the temperature rises, and we can do a thermal analysis, like how exactly is at what exactly particular location that hotspot generation will be there, and which cell will fail first, and how it will affect the failure of the neighboring cells. Such kind of different simulation scenarios we can do by these options of thermal event when it comes to thermal runaway management. And before concluding this session, so I have shown you what kind of different scales, batteries, geometries, thermal analysis, thermal management strategies we can model. We'll go for a quick demonstration of air versus phase change material, how exactly you can model that with COMSOL. But before that, I would like to conclude the presentation part, and you can check our more detailed resources for battery related to batteries from our different blog posts, videos, user stories, and different models built in COMSOL for different scenarios. Because in this particular model, we have in this particular seminar, we have seen that 5 different models for this modeling and simulation of thermal management of batteries. All those models are available in our application gallery. When if you click here and go to a COMSOL website, you will get all those models, and we'll have a quick demonstration for one of the case. And before that, I would like to launch a last poll question, and please answer this question, and by that time I'll make COMSOL interface ready for the demonstration part. Okay, let's begin with the demonstration. I hope the last poll question has been launched already. And yeah, let's go to a COMSOL interface, how exactly you can start modeling a battery problem in COMSOL environment. So this is how the first interface of COMSOL looks like when you launch the COMSOL Multiphysics tool. So this is the first window which pops up. Then you can start with a modeling, new model. You can build a model from scratch, like you can take a model wizard, click on a model wizard. Then for this thermal management of a battery pack, which is a 3-dimensional study, so we'll choose a component of 3D. By selecting what kind of component we are using for this particular case. So this component can be 0D, 1D, 1D axis symmetry, 2D, 2D axis symmetry, and 3D. We have 5 options in COMSOL. So I have chosen a three-dimensional component option here because we are interested in seeing the thermal management in a battery pack whole level. So physics required here are the battery pack, which will consider the battery which is in operation, how the various losses are acting as a heat source, and how we can do a thermal analysis for that battery pack. So battery pack interface and heat transfer in solids and fluids is can be used in this for this particular case. By adding these 2 different physics, we can go for different types of analysis, time-dependent analysis, frequency perturbation analysis, or stationary state analysis. For this particular case, I'm selecting as a time-dependent analysis. By doing this, by selecting various physics, component, and the analysis type of analysis, then we comes to this kind of interface, where when you go from top to bottom, this should be the workflow for the modeling. So all the parameters like the geometry configuration, capacity of the battery, whatever you have, all the parameters you have known, we can mention that here while modeling. And moving on, after defining the parameters, we can go and build a geometry. Geometry can be built locally here in COMSOL, or you can do a geometry import. If you right click, you get an option of import where you can build any, import any geometry from other CAD software tools, or you can also build a geometry which is already built in COMSOL by importing geometry or inserting a sequence from various applications or which are built in COMSOL itself. And after building a geometry, because for this demonstration, the geometry of this particular case will be, there will be many steps, and we don't have that much time to build a geometry. So I'm demonstrating a various steps required for the modeling, and then we'll directly go with a built model in COMSOL with results. So after defining geometry, next comes with the materials. So especially for the battery, we have a dedicated material library. In material library of battery of COMSOL, we have different materials which are defined in COMSOL, which has all the properties required for the modeling. Like in case of lithium ion battery, if when the negative electrode is graphite, you can select the graphite as a negative electrode. And for the positive electrode, you can select LCO, LFP, LMO, different standard cathodic material, and their properties are already there. So let's suppose I take a positive electrode as a LMO. So here you can see that already the properties required for all this simulation, from the structural properties to electrochemical properties, already all are there, like such as Young's modulus, diffusion coefficient, equilibrium potentials, everything is already there in this, but just by choosing a material, it saves our effort to collect all this data for particular case of material. And in equilibrium potential, you can see that already equilibrium potential, which can be a function of temperature, we have various functions defined for that. And all those values are already there in COMSOL database when you use a material library from COMSOL. For intercalation, stress, and all, we have defined various functions, and those we are using. So here, the point I want to highlight here is that various variables which can change during a simulation are not a fixed value, but those are a different expressions which are dependent on various temperature, pressure variables. So we can select these kind of, so we have dedicated library which has so many materials when it comes to electrodes, electrolytes, and current conductors, collectors. So electrodes, we have these many electrodes which are already modeled in COMSOL. For electrolytes, again, we have all the standard electrolyte for lithium ion batteries. For lead acid batteries, we have sulfuric acid. For lumped batteries, if you are interested in getting various OC versus SOC curve, those that data is also there in our material library. So this is a well-developed material library which saves efforts for a battery modeler. After adding material, next steps comes is the battery pack. So when after building a geometry where we can use a different interfaces in batteries, where we just need a capacity of the battery, because this is lumped model, a lump based model of battery pack, where we just have to mention the initial capacity of battery and initial state of charge. After giving that, we what kind of different losses we have to consider, that we can mention, and just OC versus SOC table. Either you can build a table locally here, or you can get a such kind of observation from outside. And then we just mention what kind of losses we want to consider here. We have multiple options such as ohmic loss, activation loss, and concentration over potential loss we can consider. Typically in case of concentration over potential loss, when you have a intercalating particle which can be a spherical nature, or flake in nature, or cylindrical, you can choose a different particle type, which will again enhance our accuracy when it comes to modeling. So such kind of different options are there for the voltage loss consideration. For the capacity loss or aging phenomena addition, we can consider the capacity loss, and we can add various aging losses here. And then for the case of the short circuiting, we do have option of considering a short circuit where it is happening. And for case of thermal runaway scenario, we can add a thermal event. So such kind of different options are available for battery performance equations we are available. And then for conductors, we just have to mention which is the conductor and boundary condition potentials or current. Like you can either give a charge discharge cycling, or you can give a boundary condition in terms of power. In charge discharge, we can mention what kind of C rate charging you want to do, or what kind of current you want to draw, and for charging, what kind of current, with what current or voltage condition you want to charge. So various options for charging, discharging are there. We can select either start your mode with charging first or discharging first. Then if you have a boundary condition such as power or current density, so these are the different ground potential, current density, current, power, charge, discharge, all different kind of different boundary conditions are available. And in a negative connect, we just have to mention which are the negative connectors and which are the positive connectors. Based on all these options, you can make a battery, a set of battery sets of equation. And then in addition to that, you can add a heat transfer in solids and fluids, where we have options of adding a phase change material. So let's go to a model which is already there, because that model consists of geometry, which will save our time. So this is the same kind of model built in a 3D component of a battery, where we have considered the material for battery and the geometry. Here you can see that this is in detailed geometry, which is built in COMSOL with various steps. So here you can see that the cylindrical cells are stacked like this inside a battery pack, and over that there is a battery casing. So these are the different geometry parts, and then material. So first material, we are considering that inside the space between the two cylindrical cells, there is air. Then when the holders are made of acrylic, because these cells are to be in fixed position, so acrylic plastic is used to make this position fixed, and current conductors are made of steel. So where we need electric conductivity and heat capacity and density and thermal conductivity of this material. Then for a phase change material, we have defined a paraffin material with various properties when it is in a liquid phase compared to the solid phase. So such kind of material, this material we have built in, locally built here, and in the library we have this different option for different materials. After defining geometry, when it comes to battery pack, we just mention different like batteries, current conductors, and capacities. So here capacity and SOC is mentioned. Then OC versus SOC, we have considered from one of the experimental observation given in the published paper. And then voltage losses, we can consider the different losses, which are considered over here. The particle type we have considered is the spherical particle. And then in current conductor, as I mentioned, we have given a ground boundary condition at the one side, and we are drawing a current or giving. Yeah, for this typical case, we are drawing current. It is in a discharge mode, so we have given a C rate, and the pack is in a discharge mode. So how the temperature distribution happens at such situation, that will calculate over here. And then we just mention which are the negative connectors, positive connectors. Only just by giving so much so less input for the battery pack analysis, we can get a actual real life how the battery will how the voltage versus current will behave for this battery pack, that we'll see. And coupled with the heat transfer, it gives a thermal analysis for this battery pack, where we are using this multiphysics coupling. So in this multiphysics coupling, we are coupling our electrochemicals equations with the heat transfer equation. The various sets of the heat sources we are considered here. You can see the equation sets are here, where we are considering joule heating and heating due to mixing. And then when it comes to heat transfer, what is important is, once there are two different scenarios. One, when it is filled with air, and when it is filled with phase change material. So for the same configuration of the battery, where the capacity is same, discharge rate is same, everything is same, just the packing material is different. So we have this option where we have considered this in plane through plane in plane through plane thermal conductivities of different layers of the battery. Here you can consider the option I was discussing in presentation, that here we have options of considering different layer configuration for pouch cell, flat parallel option, and for the cylindrical cell, we need the spirally wound options. So such kind of detailed anisotropic nature of thermal conductivity, which gives us a more real thermal distribution in a battery pack, can be considered. So fluid is considered. This battery pack is in the ambient condition where the heat is flowing. So we just have to mention the heat transfer coefficient and ambient temperature. So here we can see that all these things are given, and then when the heat transfer physics is said by giving a thermal conductivity, convection like phenomena by giving a heat flux condition on the boundary, and other phenomena in the domain when it is filled with air compared to the phase change material. So we can set the heat transfer physics such like this. And then after coupling, it couple the battery pack equations to the heat transfer interface, the live coupling between these two, because when the battery is in operation, it act as a heat source, due to which the temperature changes, and then updated temperature again affects the electrochemistry of the battery pack. So it means we need a two-way coupling from heat transfer to battery pack, which is done here in the multiphysics coupling of the COMSOL. And we simulated two cases. First, when the air option was on, this fluid as air option was on, and the second when the phase change material option was on. And then when we compared these two different case scenario, we found out that the temperature management with phase change material is better than with the air. And the result can be seen like this, where we calculated the maximum temperature and average temperature in two different cases, air cooling compared with phase change material cooling. And here we observed that due to phase change material property of that particular material, the management is much better in this case compared to air case. So such kind of different analysis you can perform. We can see a different animations, how the temperature is happening, changing in 3-dimensional way, 2-dimensional way. Let's see a phase change material. So this is the case, how we can see an animation which can be built instantaneously once we have all the results for the simulation, and we can see how the temperature distribution changes inside a battery pack. So such kind of different intriguing 3D plots, 1D plot, or analysis we can do in COMSOL, and you can get in detail how the temperature varies in a battery pack when it's operation. Yeah, so that is it for this demonstration part, and now the stage is open for further answer and question for today's session, and I would like to take up on questions. Thank you so much for listening this part.
Thank you so much, Dr. Meenakshi, for that incredibly informative and engaging presentation. I'm sure our audience has taken away many valuable insights. So moving on to our Q&A session, we've received some thoughtful questions from our participants. So let's dive right in. Let me view a few questions that we have received. So one question that we have received reads as, when it comes to natural convection, considering using air domain, what is the BC used on the surface boundary of the air domain?
Okay, so here in this case, so there are two, when we give air convection as a, and we are using that boundary condition for this case of heat flux. So there are two options. When one we need is a heat transfer coefficient, second is the temperature. So ambient temperature. So this temperature can be again a function of when it's a day and it's night. So this temperature can change in a cyclic manner. So we can create a function such a way that it considers that change in temperature, and instead of giving one single value for that temperature, we can make use that function which changes according to temperature of the various conditions, and that's how the boundary condition will be updated every time the temperature is changed. And based on that, you need to do some study about how the heat transfer coefficient exactly is changing with the change in the airflow in the ambient and all. So there also we can give either a fixed value of the heat transfer coefficient, or it can be a function of again a different thing. So yeah, in COMSOL, we have this flexibility of considering either a fixed value, or this value can be again a time dependent on a various phenomena. So we can create various functions and then use that as a boundary condition. So there is no need to consider a fixed boundary condition, but variable boundary conditions can also be applied in COMSOL, and we have that flexibility of changing boundary conditions in our interface. Yeah, next question, please.
How does thermal management affect battery degradation and calendar life?
Okay, so we, as I during presentation also I highlighted that all the electrochemical reactions happening inside batteries are very much sensitive towards temperature. Again, all other aging phenomena also, like plating. When the temperature of the battery is very low, lithium plating is accelerated, or when the temperature is high, the decomposition reaction starts because those are exothermic in nature. So we know that the exothermic nature itself defines that whenever there is increase in temperature, it becomes exponentially, the rate of the reaction increases exponentially with respect to temperature. So such interlinking or cyclic phenomena or cascading phenomena triggers the various side reactions in side reactions in battery, which acts as aging phenomena in battery. So it affects the overall performance of the battery. And in calendar life also, when the batteries are stored, although those batteries are ideal, they are not doing like giving output and energy or not, still the reactions will be happening inside it, and all those reactions are temperature dependent. That's why the thermal management is very important, not only for the when batteries are in operation, but when they are in a storage or they are in idle situation. So then also the calendar aging, that's how it is affected by the temperature, like temperature of the ambient where it is stored. So both aging as well as calendar life is very much dependent on the temperature when it comes to battery. Yeah, next question, please. I can't hear you.
Sorry.
Yeah.
What was the total simulation time taken for the liquid cooling example shown in the presentation? Was it steady state or transient?
Okay, so the liquid coolant example I showed here was for 4 hours. It took 4 hours simulation and it was a time dependent. So we did study for 4 cycling. So it was for study was for the 14,000 seconds we conducted and it took I think 2 hours. So we can also see just give me a minute. I'll just confirm it. It will be hardly one. So the one example which I showed you, it took 16 minutes. The liquid cooled example will take 2 hours. Yeah. The example is already there in our platform. Whenever you download that example, or yeah, if you have a trial version of COMSOL, you can see that there will be a study node beside which the last computed time will be always there, which gives us a approximated time which was needed for our system to simulate that particular case. So at max, all the simulations, most of them can be completed in hour time, or max to max 2 to 3 hours. Yes.
Can I simulate phase change materials, PCMs, or thermal interface materials, TIMs, for passive cooling?
Okay. So for the case of phase change material, which I demonstrated already in case that, so now you know that how we can do it in COMSOL. But when it comes to thermal interface material, so in our COMSOL, we have option of boundary condition where we can give a thin layer of any film and which act as a thermal insulant and which will, thermal like conductor and which will dissipate the heat. So such kind of various boundary condition options are there in our heat transfer physics, which facilitates and gives this option of considering a different passivating method for thermal management of batteries. And I hope our time is up for today's session. Any more questions? We can take one more question for today's session and then we can.
We have received quite a lot of questions today. However, we just have time for one more, so I'll just take on one more from the audience. So a question we have received is, it says, it was a good presentation. Hearty compliments to Dr. Meenakshi, how it can be made applicable for lead acid batteries.
Okay, so for this presentation, I have not demonstrated lead acid battery, but in our application gallery, we have showcased different models for the lead acid battery. And that also, in that case also, there we can do a 3-dimensional analysis, and with every physics setup, we have coupling. So in every battery setup also, we have electrochemical coupling, which couples the heat transfer with the any battery interface, whether it's a lithium ion battery or a lead acid battery, and which gives us a thermal management for lead acid battery as well. So yeah, so we already have such built-in application models. If you go to COMSOL official website, you can browse through all those different applications and you can study those cases. Once this webinar is over, you can contact to COMSOL at the support@comsol.com, and we'll give you some more documents related and customized to your needs, so that it will demonstrate our capability when it comes to different modeling of batteries, whether it's a lithium ion battery or lead acid battery. Yeah.
Thank you so much, ma'am. We do have more questions, but unfortunately, we're out of time. So, heartfelt thank you to our audience for your active participation and thoughtful questions. And a special thanks once again to Dr. Meenakshi for her detailed and enlightening responses. As we conclude today's session, we'd like to once again thank COMSOL for their unwavering support and to all of you for joining us and making this webinar a success. We look forward to welcoming you again soon to another engaging and knowledge-packed session. The floor is now open for networking. Thank you and have a great day ahead.
Thank you so much, all of you, for attending this session.